Hi folks, welcome back to Physics with Captain Rod. I'm making this video to demonstrate how to write work energy equations when rotation of an object is involved. So we're going to imagine this spherical object here starts here at what I'm going to call position 1. It's got a certain radius here, which I guess I'll just call r. And we're going to imagine that it rolls down the hill to this location, which I'm going to call position 2. And at this instant, it's got a velocity. The center of mass is moving this way with some speed v, I'd call it vg. In addition to that, it would be rotating, presumably. Right, so it's got both a translational velocity for the center of mass and a rotational velocity as it rolls along. And what we're going to do is we're going to write out the work energy theorem for this and try to get an expression for either the angular velocity or the linear velocity here, doesn't matter which. So we just write out our good old-fashioned work energy theorem for this. We've got PE1 plus KE1 plus work equals PE2 plus KE2. All right. Now, potential energies, we would normally define a datum. I should do that first. I'm going to go ahead and define this as my datum. I'm just going to get rid of it now, though, because it's not super important in the picture. We've got a PE1 term, MGH, no PE2 term. All right, so PE1, MGH. And in this example, we'll assume this guy starts from rest just to make this a little bit simpler. I'm going to hold off on that work term till last. The PE2, again, we're at our datum. All right, the KE2. So we got to think about what's happening here. This object is undergoing both translational motion and rotational motion. That KE2 term, there's two ways we could write it out. One, we could put 1/2 mvg squared for the translational kinetic energy for the fact that the center of mass is moving with this speed. And then what we could do is tack on a rotational kinetic energy, 1/2 I omega squared, where this I is about the center of mass, g. This sum would get both kinetic energy terms, and that's perfectly viable method for doing this. Or we can express the kinetic energy with only a rotational term as long as the moment of inertia is about the instantaneous center of rotation. So hopefully you've seen my video about instantaneous center of rotation. If I were to draw like another velocity vector, like if I come up here right now, if I drew a velocity vector here, it would look something like this. And it'd be quite a bit larger than this one. And the instantaneous center of rotation is the spot at which the object is effectively rotating about. And it always makes right angles to all velocity vectors on the object. And in this example, the instantaneous center of rotation is here. Now this is true as long as it's rolling and not slipping or sliding. If it were slipping or sliding, that wouldn't be true. The instantaneous center of rotation wouldn't be here. But again, in this example, I'm trying to keep this one pretty straightforward. We're going to imagine just rolling motion the entire time. So this point is the instantaneous center of rotation. And what that means is I can express the kinetic energy as 1/2 I omega squared as long as the I is the instantaneous center of rotation. I'll put the COR there. Now, either of these are perfectly acceptable. I'm going to go ahead and use this one. So for our kinetic energy term, I'm just going to put 1/2 I omega squared, where this I is going to be about the instantaneous center of rotation, the I core. Almost too much for a subscript there, but 1/2 I omega squared, but that I, again, is going to be about this point. So that's what the work energy theorem has to say about this equation. I can clean it up quite a bit. Let's leave off the zeros. MGH equals 1/2. Now I'll start working on the I. All right, so the instantaneous center of the moment of inertia about the instantaneous center of rotation. So what I'm going to do is I'm going to use the parallel axis theorem. I'm going to start with the moment of inertia of this object about its centroid, which is 2/5 mr squared. That's the moment of inertia of a spherical type geometry. And then we're just going to tack on an m times r squared for the fact that the axis is moved. So the moment of inertia of this object about the instantaneous center of rotation is going to equal 7/5 mr squared. So I'm just going to tack that on, 7/5 mr squared. There's my moment of inertia for this animal, and then times omega squared. Now, again, the other approach, we could have used this sum, 1/2 mv squared for the translational velocity, 1/2 I omega squared for the rotational, except that this I would be the moment of inertia about g, which would be 2/5 mr squared. Right, and we'd end up with the same thing. All right, so let's see. I'll notice the mass divides out. This is going to be a 7/10, so the next line might be something like 10/7 GH equals r squared omega squared. I want to make sure I did that right. GH times 10 divided by 7. Yep. So the angular speed, and I'm just going to put the angular speed squared, is going to equal 10/7 GH over r squared. And I'm going to go ahead and call that done. I mean, suffice to say, if we had values, I could put in all those numerical values there, and we could get the final angular speed. And once we had the final angular speed, the velocity g is going to equal r times the angular velocity, because again, the instantaneous center of rotation being here, this velocity would then be r times that, and we'd be done. So anyway, relatively short, straightforward problem. I should go back and revisit that work term actually that I forgot to talk about. Let me go back and chat about that and why that thing is 0. If we look at a free body of this at just kind of some generic time frame, as usual, we've got a gravitational force down equal to mg. Oops. We've got a surface in contact. That's going to give us a normal force. It might look something like this in my picture. And you might say, oh, there's no friction. And, well, you could say that, but you would be wrong. There has to be friction in this problem. If there weren't friction in this problem, the angular velocity would stay at 0. It would slide down the entire thing, and it would maintain its orientation. The frictional force in this problem points this way. Basically, the frictional force is responsible for changing the angular velocity of this object. Now, as I go through this and I talk about work terms, we don't need to do a work term for gravity because that's what the potential energy has taken into account. You don't need a work term for the normal force because the normal always makes a right angle to the velocity of this object. Or actually, let me restate that. This point right here where the normal is applied, there's no motion in the direction of the normal, either this way or this way. So there's no work done by the normal force. And also, there is no relative motion of this point with respect to the ground. This is rolling friction. So really, there's no displacement for the frictional force. So the frictional force isn't doing work either. Generally speaking here, this work term is reserved for non-conservative forces, forces that change the net energy of the system. Friction's role here isn't one of changing energy. If this were sliding friction, if this thing were sliding down this incline, there would be temperature changes along here and here. And in that case, the work done by friction would be robbing the system of kinetic energy and turning it into internal energy. But here that's not the case. As long as there's rolling, there's no heat created, and friction's role really is one of conversion. Some of this potential energy is being converted to kinetic energy, to this term right here. So there's no work term required for the frictional force. This equation takes everything into account, and we're all good and happy. So I hope this video helps demonstrate how to write a work energy equation taking into account rolling type of motion. Have a great day.